Ready. Let's get started here. We always start Friday with a little bit of YouTube to start things off. This is we introduced and talked about the Coriolis effect. There's some good videos on YouTube about the Coriolis. I like this one's kind of okay. Sorry. That's as quiet as I can make it right there. So these guys built a little contraption and they just kind of demonstrate that MIT. What's it doing? Oh, all right. So just got to show it that you throw it back and forth, the ball travels in a straight line, and then when you start spinning it, let's go, guys. We get it. All right. You start spinning it, and you throw it. They throw it to where he was, but then he moves, so then it lands in a different place. And it kind of, basically, it just travels in a straight line, but they keep moving underneath it, right? And so, but if you see, I'll say this way, you see that it goes in a straight line. But if they put one that has a reference frame that turns with it, then you can kind of see that it appears that the ball takes a turn, like it has a curve to it. So that just travels in a straight line. That's because there is no force there to make it accelerate in the Coriolis, to make it have a Coriolis acceleration, right? You walking across the thing, you're providing a force that's counteracting this effect. So you're gonna hear, this looks like it's curving. Right? So it starts throwing. It's a fixed reference frame on the thing that's turning. So when they throw it, it appears that it's curving. And the reason it goes off to the side there is because there is no force to say, yep, you have to accelerate that direction. If back to the analogy of me walking on a merry-go-round, I'm providing a force to make sure that I counter that direction that I want to keep moving. I have to make myself go that way. I have to make myself accelerate that direction. Okay, this one is an explanation of why storms rotate one direction and why they rotate the other direction and why there's hurricanes, in fact.
Picture a circle. Here's its center, here's point A, and here's point B. Point A is twice the distance from the center of the circle than point B. Oh yeah, and it spins from its center. In 2 seconds, both points do one full revolution. But to go all the way around, point A has to go this far, while point B only has to go this far. And we all know if something travels a greater distance in a shorter amount of time, it must be going faster. So point A must be moving faster than point B. Okay, now swap out this flat circle for the Earth, and the same thing is true. All points closer to the center, say like someone in Greenland, will be spinning slower when compared to points spinning further away from it, say like people in Brazil, closer to the equator. So if we look at it all flattened out, we can picture something like this. Arrows at the equator travel faster than arrows at the 45-degree line, like we just observed. Now imagine you're a cloud that formed here on the equator. You'll have the same velocity as the Earth, but then a gust of wind sweeps you to the north, where the Earth isn't spinning as fast. Due to inertia, your speed remains the same. You don't get any faster, but everything around you is literally traveling slower, so you, relative to the ground, move ahead of everything else. If you're a cloud that forms at the 45-degree line, you'll also have the same speed as everything around you, but if you drift down to the equator, you'll be moving slower than the ground underneath you, so you'll fall behind. And the same things for the southern hemisphere. Moving towards the equator always results in falling behind, while moving away results in pushing ahead. Okay, now imagine a low-pressure cell. That means all the air around it will get sucked into the center. But the air coming from the equator will be traveling faster, so it will deflect to the right, while the air coming from the poles will be moving slower, so they'll fall behind and deflect to the left. What this results in is a circular air current spinning counterclockwise, and that's exactly what hurricanes are, low-pressure cells spinning because of the Coriolis effect. Moving this example down to the southern hemisphere, things are reversed. A low-pressure cell will still suck in the surrounding air, but now the air coming from above will be moving faster, again deflecting to the right, while the air coming from below is moving slower, again falling behind by moving to the left. This results in a clockwise spin, which is why storms in the southern hemisphere spin this way. And that's about it. It's a short video, and that's kind of the point. I hope you got what you came for. And the Coriolis effect doesn't really influence toilets, they're just really too small, and the direction of the spin more depends on the placements of jets inside the toilet. But that's it, that's the Coriolis effect. If you liked this short and to the point video, give this
We did it. We came what we wanted for and we got it, right? This one's less cool. You can't really take this one to a party tonight and like demonstrate like the slinky, right? But you could, I guess. You could come up with something. just say, start talking about hurricanes. Did you know the hurricanes rotate one direction in the southern hemisphere versus the northern hemisphere? Okay, so we're on a new subject here. Honestly, I always have such a relief when I start this section because we put away like all those integrals and stuff, right? I don't like that. I don't like the integrals. I don't like the first part of this class. It is a lot of, as you saw in this last homework or are seeing on this homework you're working on right now. There's a lot of like, what do I do with this? Where do I start? What's going on here? Which variable do I do? Do I take there's that one problem where like, I'm taking the derivative of something with respect to time, but I'm taking the derivative and it's theta on the inside, and so weird stuff happens, right? I don't like it. This stuff now, things get really structured, right? Very structured, laid out. I really think from here on out, it's a breeze. It's a breeze. But it's also not gonna be complete review. Some review, but then also some new stuff. Okay, so kinetics now. To this point, we've said very little about forces, right? We just talked about the geometry of motion, that's kinematics, right? We need that stuff. We're still going to use that stuff as we move forward, but there's no mention of forces. Now, though, we get it into forces and kinetics. We're going to do three methods in kinetics. We're going to do what we call FMA, right? Force, mass, acceleration. We're also going to do work energy, right? That's my favorite. And then we're going to do impulse momentum, right? And so that's kind of our roadmap as we move forward, right? We're also going to do the three coordinate systems for each one of these things as well, at least the F equals ma. We're going to start it out with Cartesian coordinates, then we're going to do normal tangent polar coordinates. Okay, so kind of just a roadmap of where we're headed. So Newton's second law, right? This is the FMA method that I just mentioned. It's the most straightforward way of solving these things. What Newton's second law says is the sum of all the external forces is equal to mass times acceleration. Right? And these are vector equations. On an exam once, we asked, what's Newton's second law? And someone wrote sum of the forces equal mass times acceleration, which I thought that's pretty funny. Like sum, S-O-M-E, sum of the forces equal mass times acceleration. Not that sum, okay? S-U-M, the sum of the forces equal mass times acceleration. You guys are unimpressed by that joke, but it is, but it was really funny at the time. You have to trust me, right? When I was grading it one night and I saw that, I was like, ha ha, and I showed all my colleagues, right? It was funny. You got to trust me. Okay. So what we're going to do, these external forces, these things come from the free body diagrams. If you hated free body diagrams and statics, you're really going to hate them here. They're super important. You need them. And then we're going to end up getting in equations for accelerations. And then at that point, it becomes kinematics. So I pointed that out a couple of times, like, oh, hey, look, here's an acceleration equation. That acceleration equation, now we're not going to start out with that given. We're going to have to derive that acceleration equation ourselves. And then once you get that acceleration equation, then you just do kinematics like we've done so far. And again, we're going to do three coordinate systems. Three coordinate systems. Right? The three coordinate systems are going to be Cartesian, normal tangent, and then polar. The students in the other class I'm teaching a grad level class on pre-stressed concrete, and then they were complaining about my handwriting, and they're like, why don't you just write neater? And I was like, that's very easy to say. It's very difficult to do, right? If you ever say, oh, just try to write cleaner. So I'm trying to write cleaner. I'm just focus more on the thing. I think in order for me to do it, I'm gonna have to not talk while I'm writing. Let's try that for a little bit. Just years of weird shit going on in this, right? Systems, I got a capital T, a capital E, right? Lowercase y. There's all this mixture of stuff, right? Cartesian. I mean, look at Cartesian for God's sakes, right? Right? There's a capital A in there, but a lowercase I, right? Like, what the hell's going on in there, right? This is weird shit. All right, I apologize, but you can read it, right? You know, someone suggested just switching over and then writing in all caps at all times, because then that's not how I usually do it. So then that will force me to start writing. All right, we'll see. Can't teach an old dog new tricks. I'm gonna try though. I'm gonna try to write cleaner. Okay. And then we mentioned this last time. The other thing when you're like unartistic, the more you focus on something, the worse it becomes, right? So I'm going to try to write cleaner, but then it may end up worse. So there's nothing you can do. Okay. Cartesian coordinate systems. We're going to start out with that one. Cartesian. This one's easy. Some of the forces, the external forces, this is equal to mass times acceleration. That's just, and then we just treat these things as vectors. If we explode this vector, what we get is some of the forces in the x direction, in the I, plus some of the forces y in the j, plus some of the forces z in the k, is equal to mass times acceleration x in the I, plus mass times acceleration y in the j, plus mass times acceleration z in the k. You just expand those vectors out. Again, those can be written in different forms. I like the IJK, especially for these types of problems. If you remember how matrix math or vector math works, right? Everything in the I direction have to be equal to each other, right? So those two guys are equal to each other. Everything in the J direction has to be equal to each other, and everything in the K direction has to be equal to each other. These guys, right? And so what you end up with is just 3 equations. That's what these guys are. Okay. Some of the forces in the X is mass times acceleration in the X. Some of the forces in the y is mass acceleration in the y, and some of the forces z is mass acceleration in z. Okay? These things are what we call our equations of motion. Right? And we actually call them EOMs. Or equations of motion. Okay. Now, the other thing I do, like I said, I try to lay these things out and be as like procedural as possible. So I'm just gonna give you some like a checklist, if you will, for what you need to do for your free body diagrams, right? I say these are required. I think statics does the same thing. You must draw a free body diagram. I absolutely insist on it. It's worth points. If you don't include a free body diagram in one of these problems, I will dock you for it, right? You know, I'm gonna have Axel dock you for it in your homework if you don't include it. That's just how important they are. You guys were told that in statics a lot and you probably didn't believe it, but in this case, absolutely, it's so important to write that free body diagram because it keeps our mind clear and it lets us see everything that's acting on it, and we can solve the problems easier if we have a good free body diagram. I always, like I said, I lay out a procedure here, or a checklist. I call it a checklist more than because you can do them in any order, really. Uh-oh. All right, little checklist. I'm gonna go 1. We're gonna isolate the particle. All right, that's all we're doing with right now is particle or object. First thing you do, take everything off of there and isolate that sucker. Right? Then we replace supports with appropriate forces or moments. We sketch applied loads, forces, and we pick a coordinate system. And label it on diagram. Again, it doesn't have to be done in this order. And then label dimensions, angles, etc. I'm gonna move some stuff around here real quick. Cool. Okay, that's our process, right? Again, you know, once you get good at this, you won't need to come back and look here. But I just, as we're learning, you guys are learning these things. We're gonna go through, and I'm gonna kind of step by step do this when we draw a free body diagram, right? Some key things in there, right? Obviously, isolating the object, drawing the appropriate forces, but also the coordinate system. Label it, because we're going to have 3 different coordinate systems that we're going to be dealing with. But labeling your coordinate system on the diagram, the dimensions and angles and stuff like that in the diagram, huge to help out. Okay, so that's our free body diagram. I'm also going to give you a procedure to follow for solving these types of problems. Right, these free body diagram or these kinetics problems, the FMA kinetics problems. First thing we're going to do is draw a free body diagram. Hence, us talking about free body diagrams a second ago. Second thing we're going to do is write down EOMs, equations of motion. Third thing we're going to do is kinematics. I'm going to say as required. Sometimes they're not. Kinematics are pretty simple, but sometimes they're super important, especially when we get into 2D rigid body stuff. The kinematic step becomes pretty important. And then the last step is to solve. Okay. And I'm going to try to do this at each time. Every solution method we do, I'm going to try to give you a procedure so you'll be like, oh, what do I do? And really, if you stick to this procedure, right, and then you kind of are very detail-oriented about working your way through this procedure, the first thing that's probably going to happen is you're probably going to get the right answer, right? And the second thing is, if you did get a wrong answer, when I'm grading it, I'll be looking at it going, oh, look, they followed the procedure. So I'm going to, I'm going to give them the benefit of the doubt. And if they've made a mistake, I'll be able to look back and see where you made the mistake and appropriately give you partial credit for things, okay? So just be very careful about that. Try to follow the procedure. Do not trust your intuition. Don't just look at it and go, oh, I know what the answer is, and then just write like one equation. Just stick to this procedure. It really will help you. Maybe you might look at it right now and be like, this is a little overkill doing this procedure for some of the problems we're going to be doing here. It probably is. But when we get into 2D rigid bodies and 3D rigid bodies and stuff gets really weird, following this procedure is going to be super critical, super important to do. Okay. It'll lead you to the right answers. Okay, let's do an example. This is very similar to an example that we did in just kinematics, but in this case, it's just a spring, right? There's a mass hanging from a spring, and it's going to be released, and it's asked, some information about it. And I think this is the same one here. Yep. Okay. And then. And we remember we did a problem similar to this a couple weeks ago, and I said, and what they did in that case, that we started out with the acceleration equation and then went from there. In this case, there is no acceleration equation. It just tells us information about the system over here, right? And then asks us some questions about it. So we have to try to solve it. This is where those equations we just derived came up in this process. Okay, so back to our procedure. Our procedure said, right, you look at it, it's like, what do I do? And part of it just helped guide you a little bit. You look at this and go, what the hell do I do? Right? I kind of know where I need to go, but I'll go to the procedure. Just blankly, purposely immediately go to doing that procedure. First step in the procedure says draw a free body diagram. Okay, so we're going to draw a free body diagram for this. And when I solve these things too, I label each step. 1, free body diagram. Okay, isolate the object. Particles, super easy, right? My isolated object could be just a dot, right? It's just a concentrated map. So I'm going to do it that way, right? You could draw the box if you wanted to make it more clear. I oftentimes, for particles, just draw the dot, okay? Forces acting on this dot, this mass. What's that? Gravity in the spring. Yep, gravity in the spring. So we've got this guy doing this. Mass times gravity. And then we have the spring doing this. I call that Fs, force from the spring. Okay. What is the magnitude of that force going to be? Or what's that force going to be? K times the distance that it's stretched, right? K times that will tell us how much force that's going to be, okay? And so we'll call that Kx, right? This is just a 1D problem. So I've labeled, there's no other supports, there's those forces, I put them in there. You got mass times gravity, I got the spring going up, right? That was step 2, free body diagrams. Replace supports with appropriate forces, sketch applied loads or forces. We're on step 3. Pick coordinate system and label it on the diagram. Like I said, it's just a 1D problem. For whatever reason, I chose to do this with X, I chose my variable. A lot of people would want to use Y. I'm not a lot of people. I'm cool. Keep things interesting. I'm going to label, that's my coordinate system. I'm going to say it's isolated there, and then I'm going to have X positive down. That's kind of standard in a lot of scenarios with springs and stuff. So anyways, X is going down. When we talk about deflections and beams, we always talk about the beam deflection being positive down, which is kind of weird, but that's what we do. So anyways, I've chosen my coordinate system. I've said it's going that direction. And the last step says, pick coordinates, says label dimensions, angles, etc. Not really any labels. There's no dimensions or anything like that that are super interesting at this point, interesting or relevant here. So there's our free body diagram. Okay. Second step. Step 2. Right. What was it? Write an equation of motion. That it says write down equations of motion. Right. And only one really valid one here. Right. Because the other directions are all 0. 0 m's. Sum of the forces in the x direction is equal to mass times acceleration in the x direction. That's our equation of motion. At this point right here, though, we can write down what the forces in the x direction are. What are the forces in the x direction? You look at my free body diagram. Right? You literally just jump over to your free body diagram and say, hey, what forces are acting on this? Well, I've got mg acting in the positive x direction, so that's going to be positive, and then I got kx acting in the negative direction. Right? It's acting up that direction. So you just expand what those forces are. You just sum those forces. So this will be mg minus k times x is equal to max. Okay. Let me note what some of these variables are, right? So at that point too, again, our goal is to be getting an acceleration of, we're trying to solve for the acceleration, right? We're trying to come up with an acceleration equation. So at this point, you just solve for ax, just algebra. Ax is equal to g minus k over m times x. Right, and at this point right now, that's our equation of motion. What kind of equation of motion is this? Or sorry, acceleration equation is this? What kind is that? It's acceleration of function of position, right? X is a position, so it's acceleration of function of position. You open up your kinematic stuff and say, what do I do when I have accelerations function of positions? And then you solve it that way, okay? So now it just switches over to kinematics, which we've been doing so far in the class, right? So in this case, my kinematics kinematics. We got AX is equal to, I went back in my notes to see how I solve acceleration to function position. We have to use this chain rule. dv dt, oh sorry, dv dx, dx dt. This dx dt is just the velocity. This becomes v times dv dx. Put all the x's on one spot, so this just becomes, my ax is, we just solve for it, g minus k over m times x dx is equal to v dv. Integrate both sides. This guy's going from 0, we're after the velocity at 0.3. So I know my bounds of my x. My x is going from 0 to 0.3, and my bounds on the other side are going from 0 to VF. I'm after this VF right here. That's what I'm after. Okay, and you just carry out that integral and solve for VF. We get VF 1.37 meters per second. Right, and I would say this last step right here, right, this is our solve. Our solution method at each one of those, right, had drawing a free body diagram, writing our equations of motion, doing our kinematics, and then solving. So the last step right there is just the solving. Right. So you would have to take that integral and then carry out the definite integral and go that way. I did that all with my calculator. Start learning your calculator. Super helpful. All right, we got time for another one. Everybody cool? Any questions on that one? See, it's pretty straightforward, right? You follow that procedure, it leads you there. This is a little bit more complicated because it's got a little integral in there, right? We don't want to get away from integrals, but that one ended up with the integral. Okay. No integral in this one. Okay. So this one, we got a slope, right? We've got this little block, right? There's that little blue block right there. Let me make it blue here. Okay. The little blue block is kind of sliding down. Is that thing frictionless? I think it's frictionless, right? Neglect friction, right? So you can imagine if that's, if that string here, right, that string goes like this around a pulley and then down. And you can imagine if that string wasn't there, this block would just want to slide down like that from right to left. Or if I'm not pulling on that string at all, if that string is slack, right, then this block will slide down there. But you can imagine if I pulled on this thing, I could slow it down if I pull on it a little bit, or even if I pull on it hard enough, it's actually going to go up, right? If I pull on this thing down, crank that thing down, this block is going to want to move up to the right, right? And so what we're asked to find is the P that's required to cause the block to accelerate up at 2 meters per second and down at 2 meters per second squared, okay? So what is the, let's solve that, right? How do we go about solving? You might look at it and you're like, oh my God, what do I do? What do I do? There's so much stuff. There's a lot going on. How would I do this problem? Don't panic. Stick to the plan. Go to that and start the process, right? So what's the first step? Free body diagram. Every time. Free body diagram. One. Free body diagram. Okay, my free body diagram is going to look, we're going to isolate that block, that sucker right there. Hey, what do we got acting on that? If you ever want to do it, whenever I ask that question, you just throw out gravity, okay? Because that's almost every single problem. You just be like, gravity. You could be the one person that yells out, gravity. Yeah, there we go. Gravity is acting on that. It's not always. I'm going to set you up sometime. I'm going to set you up, right? Because there's going to be some cases there isn't gravity, but in this case, absolutely gravity. Gravity's going this way. Okay? What else? Yep, normal. Someone said normal. Somebody had the yep. So let's get both of those in there. Normal. Uh-oh. Normal force. And then you said the tension in the rope, right? So we got that normal force coming up like that. Okay, you could draw it underneath. Yeah, I'm gonna move it. You could draw it in two different places if you want. I just want to leave room to kind of break one of these things out. So normal force could be like that. You could draw it underneath. You could put it wherever you want. Okay, tension in the rope. That's going to act the same direction as gravity here. So just to keep it clean, I'll put it down here. That's going to be our force P. But then also there's going to be this P that goes this direction too. Right. The way that thing works is it goes around that corner. Pulling it down that way, but then it's also going to have an effect up to the right too. Kind of equal and opposite there. Okay. Anything else? I think that's it, right? Yep. Yeah, that's right. Yeah. So that's it for forces. But then now we got to put a coordinate system in here, right? That's the next step, and then clearly label it. I hate doing this. I hate it, but then it really makes things better sometimes when you have these slopes like this. It's nice to like rotate our coordinate system. Right? You may hate that. It's like, why the hell am I rotated? You could do it the other way. You could set it up so that you have an unrotated coordinate system, and it'll work out fine. It's just a little cleaner if you rotate it. So I'm going to rotate it. And usually, you know, there's later on we do some problems, and then students mess up because they rotate their coordinate systems when they shouldn't have rotated them. So just be very careful. Usually if you have like a slope like this with something sliding down it, if you're not using work energy, if you're not doing work energy or impulse momentum or something, rotate your coordinate system does make it work a little bit better. Okay, so let's do that. So I'm going to do that. I'm going to do it like this. I'm going to say my x coordinate system is going to be this direction. Oh, my x is going to go like this. And then my y is going to be going this way. Those should be orthogonal. They're drawn a little off there, but they should be 90 degrees to each other. Okay. Clearly labeled my coordinate system. Okay. The next step is to put any angles or dimensions and stuff in here. And there are some stuff going on. There is some angles that we can label in here. Okay. This guy. Oh, I'm going to go a different color here. I'm going to say this guy right here. Oh, thread here. This angle right here is 20. Okay. And sometimes I like to do this on my free body diagram. Sometimes I like to take, well, so this tension force right here, that lines up in the x direction, fine, right? So that lines directly up. The normal force lines directly up with the y direction, that's good. These two though, my P and my, I didn't label that, mass times gravity. Okay, these two though, right, they don't line up with the x and y coordinates. So they're gonna have an x component and a y component. Right, and again, this gets a little weird because usually you think your mass times gravity being in the y direction, but since we rotated it, it's not. So sometimes at this step, I like to put on these diagrams like what their components are, just to kind of clean things up. So let's do that, just to keep it nice and clean. So we're going to break these guys down into their two components. Right, this guy's going to have that guy. Right, that lines up in the y direction, and then this guy is in the x direction. Same thing here. Right? Just to kind of show that, which ones are in the x, what components are in the x and the y. Okay. So then I should probably put those angles in there as well, right? The way I do it, and you can come up with your own way, right? But like, this guy's coming down. We know that total thing is 90. So this is 20. That one's not 20. This one is 20, right? That's what I do. Okay, that's what I do. I just work my way around. Okay? This one's 20. This one's not 20. This one is 20, right? So I'm going to put that as a 20. We're going to do that a lot this semester. You'll hear me be like, that one's not, that one is, that one isn't, right? And then this one here too will be 20. Right? 'Cause there's a 90 and then there's another 90 and then, right? There's all different rules back in geometry about which one's which and stuff like that, right? That's how I do it. Is 20, not 20, is 20. Then I don't have to do any math. Like 90 minus 20, yeah.
So is it assumed that the normal P force is you don't have to draw 90?
Correct. Yeah, it's assumed. My drawing's not good, but yes. But I mean, I shouldn't say that. That's a good drawing, but that's real good for me. Look how clean that is, right? Right. But it is, they should be 90. But yeah, the normal in this particular case will be perpendicular to the surface. It'll always be perpendicular to the surface. Yep. Great question though. Okay, that's my free body diagram. Tight free body diagram, ready to go. Okay. So then, second step, write our equations of motion and expand things out. EOMs and expanding. Right? So we say, yep, that's sum of the forces in the x direction. And at that point, what you do is you look for all the forces in the x direction. I just go right to this diagram right here. And I say, yep, I got P that's going in the positive x direction. So I write that, P minus, then I have this, right? So I've got this P, I've got this part of my mass times gravity, and I got this part of my P, my applied P. Right? So it's really clear like what is supposed to be in that x direction. Right? Those three forces will be in the x direction. So we got P, and with geometry, this is going to be mg sine 20. Okay, and then we're going to have minus P times sine 20. And all of that is equal to mass times acceleration in the x direction. Okay. And then gotta be careful of signs, but our nice, beautiful free body diagram that documents everything shows us that one's going to the right and the other two are going to the left. Right? Now we write the equation of motion in the y direction. Equals n. We got a normal force. So yeah, just to highlight them, we got the normal force here. We've got this part of mass times gravity, and we got this part of our P. So there's our y forces. Okay. So it'll be n minus mg cosine 30. 3 squiggles on my 3, 30. Minus, yeah, I wasn't finished yet. I was getting to that. It worked. Trust me, it's important to do it that way. See, I told you that's a funny joke. I'm gonna keep it up, right? MG cosine, and again, even when you stop thinking it's funny, I'm gonna keep doing it. Cosine 20. I don't make mistakes. N minus mg cosine 20 minus p cosine 20 equals may. Oh, yeah, and actually, what's interesting? What is the acceleration in the y direction? 0, right? It's not going to fly off. When we pull that thing, it isn't going to fly off in the y direction, right? It's not going to accelerate in the y direction. The way we have y drawn here, right? Again, your intuition says y is going up and down, but the way we did our coordinate system, it's not. So this whole thing is equal to 0 here. Right? But that's statics right there. It's statics in that direction. Okay. All right. So we're there. We're to this point right here. Right? We're like, what is it that we, how do we solve it now? We're trying to figure out where it accelerates up at 2 meters per second or accelerates down at 2 meters per second. How do you think you would do that?
Positive x and negative x.
Yeah, that's right. Positive A, and they give us the A of x. So right here, right? That AX, that's going to be given, right? That's told. We're told what that is, right? We're trying to solve for it when it's equal to 2, and then we solve for it when it's equal to -2, right? Because one's going to be going up, so that's to be the +2, and there's one coming down, which is the -2, right? So what that'll look like for the first part of the problem, what you do is you say this. You say P minus mg. Oh, why did I draw such a weird G? mg sine 20 minus P sine 20 is equal to our mass times 2. This is accelerate up. Right, that's just algebra at that point. We know the mass, we know gravity, we know mass, gravity, we know sine angle. The only unknown in this is that P, right? So we're after this guy right here, right? We're after this guy. And this guy. That's the only unknown. Everything else is known, so it's just algebra, which is code for, I plug it in my calculator, and so my P ends up being 1.63. Okay, that's for it accelerating up. The second part of the problem would be P minus mg sine of 20 minus P sine of 20 is equal to m times -2 on the right-hand side there. And then excel down. And my P in this case ends up being equal to 0.412. Nailed it. Okay, so that last step obviously is solve, right? Just to highlight it. Is that step 4? Okay, the other thing is that step 3 is kinematics, right? And did we do kinematics, geometry of motion? Kind of we did. The kinematics in this case would be looking at it and going, oh, what do I do for my accelerations, right? And anything to do with geometry. Like we had to pause for a second and say, hey, what do I do with this 2 and -2 thing that's going on? And that's just because I'm looking at it, I was like, okay, if it's going to accelerate up, it's going to be +2. If it's accelerate down, it's going to be -2. That's kinematics, right? It's in there. It's just very light in this case, but it is in there, right? Setting these two things. Maybe I'll label that as such. I'll go red. We'll call that my kinematics. Like I said, sometimes it's used more obvious than other ways, and that's how it was used right there. You need them in some capacity to do some geometry of motion. Okay. All right. I mean, that's the Cartesian coordinate system. The next one we'll wait until Wednesday. Right? Remember, there's no class on Monday. I have to go to a funeral. If between now and then I have a chance to record a lecture, I will. If not, we'll save a recorded lecture from later if we're behind. Right now, we're sitting okay with timing, but if for some reason we're going to be behind, keep it posted. If I end up posting a lecture, it'll be doing some problems like this, and I'll do some examples with this, and I'll let you know as soon as I get it done. Right? I'll put it on D2L or something like that. Okay, cool. Have a good weekend, everyone.
Can I ask you a question
Yeah?
about that integral?
Yeah.
Is that the correct method for that first question, not the second one?
Let's see. For this one?
Yeah.
Yeah. So you say integrate. Y. Yep. Oh, you even put it in the solve too, right?
Yeah.
And then
Trying
you
to
did
figure
it.
it out.
Yeah, you got it right there. I mean, that's the answer.
It plus or minus, and that's just
Yep.
because it's that square to be square.
Yep. Yeah, that's right. It works either way. Yeah, and so you got the 1.37 right out of that.
Sweet. Thank you very much.
Damn right.
This is
It's
awesome.
sick, right? It is sick.
Not to be a stickler and fuck with you, but I have to.
Yeah.
Right? So in the wording of that question, it didn't say up the ramp. It said up or down. Up being defined as opposite of
Oh,
gravity, and down
you're
being
right.
defined
You're right.
with
Yeah.
gravity.
You're right.
That was a little weird.
Yeah, I should. Man, I wasn't done yet. The ramp is. It should say up the ramp or down the ramp. It should say that. Yep.
Here, you got your.
Yeah,
hoping it
yeah, because then it'd just be geometry to figure out what that equated in the. Yeah, I get it. I'll fix it for future generations.
I don't know who assigned this problem, but
Yeah.
when I was going through it and talking with Jamie about it. You were given like an R of theta,
Yep.
I think.
Yep.
And the answer in working through this with like a weird chain rule situation was like a dd theta of 10 theta, and then how he rolled through it was like you have d 10 theta dt, and then you could pull out the 10, and then it was d theta
yeah,
dt.
maybe
is
it's the way he's
what you
describing it incorrectly. It is.
like that seems like
What it is, it's the chain. It's the chain rule because you're taking the derivative. What you really want is the time is dr dt, right? Right. You want dr
And the
dt,
R is 10 theta.
but then
so you just
yeah,
replace
exactly.
the
So
R
then
with 10 theta.
r, yeah, this is equal to d of 10 theta dt. And so what a lot of people do is they're like, oh, I'm going to take the derivative with respect to theta, but you can't take the derivative because theta is a function of time as well.
yeah.
And so then that's where like that chain rule comes in, where it's like dr d theta dt. And so then you take the derivative with respect to theta, but then you have to multiply it by d theta with respect to time. And so that's where this becomes dr d theta would be 10 and then
d
theta dot.
theta dt is
Yeah,
okay.
10 times theta dot.
Okay,
And
so you're not really pulling out a 10, you're actually
no, it's the
you are
chain rule.
differentiating.
Yeah,
Because
and it-
otherwise, if I look at it as like d theta of 10 theta,
Yeah.
with like
So
then
that's how you get, because this equals
Yes.
10,
Yes.
and then
d theta
because
dt
the chain rule.
Yep, and d
Yeah,
theta
it is,
dt is
so-
just theta dot, and so it's weird, and so it's more of like a math thing that's happening. You're taking the derivative of something that's a function of time, because theta is a function of time, but it so actually your calculator, if you have a fancy cal, you could do that. You could set up. I'm going to take the derivative of a variable that's a function of time with respect to time, and it'll do that. It'll take the derivative of the first thing and then do the other thing. So.
Because otherwise, if I almost think about it as like a partial derivative.